Let's go. Bailey, wake up. Miss Powers, thank you. We're gonna be hacking the blockchain for fun and profit. Well, theoretical profit. We'll see a little bit. All right. For those who don't know me, my name is Dominic. I also go by Acrylic. I'm a second year CSEC student, or maybe third year. I don't really actually know now. I'm confused about that. But it's my first year at RIT. I'm also a red team content engineer and researcher at TryHackMe. I also contract for BC Security as a course instructor. So with that, I've spoken and instructed at Black Hat USA, Black Hat Europe, and DEF CON. So just a little bit about what we're going to cover today. We're going to just do a little introduction about the blockchain, smart contracts, and then we're going to move into kind of what smart contracts look like, how they're kind of scripted, and what their functionality is. And then we'll look at a few different contract vulnerabilities, et cetera. All right, so first, the blockchain. Can anybody kind of answer, just give me a general definition of what the blockchain is? There you go. We're sure we're gonna go with that. Funny linked lists with hashing. So the definition that I prefer is digital database or ledger distributed among nodes of a peer-to-peer network. Yeah, that's a really bougie definition. So what I actually prefer. So it's just going to act as a database to store information. It's going to be shared among members of a network with no one entity in control. So it's going to be decentralized. That's just the aim of it, and the goal of it is to just allow the digital information to be recorded or distributed, but not edited by any one entity. And so every single peer of a blockchain network is going to be expected to maintain the integrity of the blockchain. So that is that if there is a malicious actor inside the blockchain, that one person or that one peer cannot affect the rest of the chain. I forgot I put that in there. All right, so smart contracts. So really, to have an actual application of the blockchain, to have some kind of tokens, et cetera, to do something with it, there are often things called smart contracts that are used to negotiate things like cryptocurrency. And so these are done through what's called a DeFi application, or a decentralized finance application. So it's going to be used to support some kind of cryptocurrency on the blockchain and really facilitate some kind of exchange between those entities. And so a smart contract is very similar to just like a normal kind of contract in which there are two entities that want to in some way transact or exchange some kind of information, some kind of data, or some kind of agreements. That's the same thing that a smart contract is doing, except it's doing it for cryptocurrency or on the blockchain. So smart contracts, they're very comparable to kind of any other application or program created by a scripting language. So things like Bash, JavaScript, et cetera. And so there's three kind of main smart contract and blockchain centralized and focused languages. Solidity, which is what most of the smart contracts that you're going to see in this presentation will be ran in. There's also Viper, and that's a lot of wind, and Yule. But they can even be ran in other languages with libraries. So Rust, if Mr. Joe is here, he's not here, but he'll probably woo, and JavaScript as well. So just like most applications or scripts, et cetera, they're going to wait for some kind of conditions to be met, and they'll execute whatever actions that you want to perform. So those may be things like checking out, withdrawing, depositing, et cetera. Checking your balance. So kind of how smart contracts work is they're very similar to kind of object-oriented concepts like classes. They follow a lot of the same structure with kind of methods and constructors, et cetera. And so there will be various fields of a smart contract encapsulated in a class, which will just be the contract class. And most of them will be private fields, just as you want with proper encapsulation in an object-oriented class. So like I said, just a few of the behaviors or of the methods of a contract. You may want something like checking your balance, depositing, withdrawing, et cetera. So here's an example of a Solidity contract. This is a little intimidating at first, but it's really not a lot. So here at the very first line, we see contract ether store. That's just going to that'll be just like our kind of class declaration. It's telling us, hey, we want to encapsulate everything here. We also just see a mapping here of an address to a unsigned integer and a few different methods or behaviors of this. So you see we're going to have a deposit. We'll take some kind of amount and put it into the overall contract's balance. Withdrawal function where it will take the balance of that specific account and then withdraw it, and then just a get balance function as well. So how each contract is going to have to kind of interact from one contract to another. So every single transaction is going to have two separate contracts, one being the accounts contract and then the other being the kind of pools contract, depending on kind of what system or architecture, et cetera, you're using. So here we have contract B, which would be some kind of accounts or users contract, and we have contract A, which would be some kind of pool. So here we're just depositing 1 ether, and then the total balance of the contract will be 200 ether, and then the the balance for the user will be 1. So here we see that contract B, it's already deposited its ether, and now it wants to withdraw. So it will check any conditions that it needs to meet. So in this case, it's going to be the balance is not empty, and it will send back any kind of ether that it either requested or the entire balance back to contract A. And so we see that in the previous slide, it deposited the 1 ether, and now it's withdrawing the 1 ether. So at this point, before the withdrawal actually finishes, there's this point at which in a smart contract, it allows it to fall back or continue exiting other calls before the withdrawal function finishes. So this kind of brings us into our first kind of vulnerability, and this is going to be called, apparently it's not going to bring us into our next vulnerability, sorry. So just recapping what we saw, we know that there's 2 conditions that need to be met. The balance needs to be greater than 0 for whatever the account contract is, and it's going to send the Ethereum. But because these other calls can happen before the withdrawal function finishes, and so if we look back at here, we see this kind of line here of balances of the message.sender is equal to 0. And before this line can execute, you have the opportunity to send other fallback functions or other functions here. So if you kind of think about what we can do with that, it introduces something called reentrancy, in which a malicious contract can use a fallback function to continue withdrawing from contract's entire balance, not just the account's balance. So we'll use the account's balance to determine how much it can go ahead and withdraw at one time, but it'll just continue doing that and not internally change the account's balance, and so that takes it from the entire pool's balance until it goes to 0. So here we just see again, we're going ahead and depositing from contract B, our malicious function, to contract A or our pool. And then we want to also withdraw whatever we just deposited. So that 1 ether we're depositing, and then we're withdrawing that. So contract A, or the kind of pool function, is going to check that that balance is greater than 0. We just deposited that 1 ether, so that will be fine. And it's going to go ahead and send back the account balance, and then set the account balance to 0. So we kind of see here that's going ahead and sending that withdrawal function back. But what can happen is before this ever even hits, it's sending back the account balance, and then the function is going ahead and sending back a fallback function, which is calling the withdrawal function again. So we see this kind of infinite loop here, and it's never actually hitting this account balance to 0 line here. So here is the kind of code again for this ether store, which is vulnerable to this reentrancy attack. So here we see that's saying the balance to whatever its internal balance or internal variable for what the sender's balance is. And it's going ahead and sending back that balance. But here is where we would go ahead and send our fallback functions, and it can never reach this line here. So here's how we would go ahead, and this would be a malicious contract or an attacking contract. So we see here that's going to kind of go ahead and make a few variables for the ether store itself. So we can go ahead and interact with that contract. And we also see that it has whatever its withdrawal function is. So that's going to be the payable, or that'll be the fallback function here, and then we also see here, this is going to be like our withdrawal function. So it's going to be requiring that it's be at least greater than 1 ether, which will satisfy the first condition for the pool contract, and we'll go ahead and deposit it and then attempt to withdraw it. And then this withdrawal will jump back to the fallback function, and I'll continue withdrawing it and causing the loop. So we'll go ahead and do a little demo here. This is a new mic, so this is gonna be fun. All right, so here we have a kind of a emulation environment called Remix by Ethereum. So what this is going to do is going to allow us to kind of emulate different contracts inside of a virtual environment. So we have our first contract here, just the Ether store. Okay. And then we also have our attack contract. So what we need to do first is go ahead and compile our contracts. So we're going to jump down here, make sure that we're on the right version of Solidity. I believe after 8.10, the reentrancy vulnerability was actually kind of mitigated to a point. So 8.10 is kind of the version that we want here. So we're going to just go ahead and compile this and then compile our attack function as well. And we jump down here to this is all the VMs that we have, and then we see that we also have several accounts here as well. Thank you, Brad. All right, so all right. Yeah, looks good. All right, so we see that we have our environments, and we also see that we have our accounts. We have things like gas, which I don't know enough about smart contracts and blockchain to understand gas and all that. But we also have our contracts here. So we're going to go ahead and select our Ether store contract, and then we're just going to deploy that. So we see down here by our deployed contracts, we have all of our different functions. So our deposit function, withdraw, balances, get balance, etc. So what we're going to do, we're going to copy the address of the Ether store, change our contract to be deployed to attack A. We're going to go ahead and deploy that with the, we're going to kind of reference it with the address of the Ether store contract. So I'm going to go ahead and deploy this. Okay, actually this needs to be deployed under a different account, sorry. Deploy. All right, so now if we go back to our first account, let's say we deposit 15 Ether. We should see here that the balance is going to be 15 Ether after we've deposited it. So we can go ahead and go back to our second account, which has the attack contract deployed. We can go ahead and have some kind of small arbitrary value that's greater than 1, so I'm going to use 2. And we just go ahead and hit the attack button. And now we see that we have first our 2 Ether, and then we have the 15 Ether from the Ether store, which we didn't control that 15 Ether. That was deposited by the first account, and now our second account has the entire balance of the first contract as well. So now we've successfully kind of attacked and exploited this contract. Hopefully that was, it's a little bit of just like, do a few things here, do a few things there. So hopefully that made a little bit of comprehensive sense. So let's just, okay. There we go. All right. All right. So here we just going to see the fallback function, and then what will happen as long as the balance is greater than 1, we're just going to continue withdrawing, which is how basically it's going ahead and withdrawing those 2 Ether, and then it's just looping, and that's how we got the 17 Ether. So that's kind of the reentrancy vulnerability. And so we have another vulnerability here called an arithmetic overflow or an arithmetic underflow. And so this is at any point in which an unsigned integer is going to reach its size in bytes. And so what that's going to allow us to do, say the uint has a maximum size of 255 bytes. If we add 1 to that, or in binary 111, 111, 111, the uint will overflow and reset to 0, or all zeros in binary. In underflow, if it's at 0 and we subtract 1, it will then underflow to 255 or all ones in binary. And so here we just see the example of the uint variable of balance. It's equal to 225, and then we go ahead and add 1 to that, and it overflows. So here is an example of why this would be important. So this is a contract called lock time. And so what this is going to do is it'll allow you to deposit at any time, but for any account holder, it won't allow you to withdraw until 1 week after the last deposit. So it's going to lock you for 1 week without withdrawing. And so we see here that's using an unsigned integer for balances and lock time. And then it's going, I think I have highlights here. Yeah, so here we see our lock time uint, which will be the max of 255, right? And then we see here that's using the timestamp block to go ahead and define what that lock time is and then add it to 1 week. So it's going to be whatever the current time is plus 1 week. Okay, and then here is our withdraw function as well of the same contract. So here we see that it won't allow any account holder to withdraw unless the timestamp of the current account is greater than that lock time. So the intended behavior behind that is so there's also a method called increase lock time, and that's really only supposed to allow the contract to increase. So it really has no function to us. So we want some kind of way that we can go ahead and bypass this lock time, be able to withdraw at any time that we want to. And so with that, because this is an unsigned integer, we can go ahead and add 1, or really any kind of arbitrary value that goes ahead and overflows that unsigned integer, so that then it will reset the lock time to 0. So here we just again see the unsigned integer of lock time. We see the require function, and we just see some of the math required to go ahead and get our overflow. So here would be our malicious contract. So we see again that we're just declaring whatever our target contract is, and then we're seeing our constructor as well. A fallback function is there because for any contract interacting with some kind of pool, there has to be a fallback function there. And then we see our attack function. So we're just going to deposit any kind of arbitrary value for a majority of exploits or attacks within Solidity. You have to have some kind of deposit there, any kind of arbitrary ether value. Most of the time it's going to be greater than 1. And then we also see that we have our increased lock time here. So it's going to take whatever the max uint size is, so 255, and add 1 to it, and then subtract that from the lock time. And that will then overflow that integer for the lock time and reset it back to 0. So here, again, in Remix, we see that we have our time lock contract here, and we have our attack contract as well. So this is a 0.7... So we're just going to select the 0.76 version here, and then we're going to compile. I'm just going to make sure. So I'm just going to change the VM since the other one had the old contracts in there. And I'll go ahead and compile time lock and compile the other contract. So here, if I go ahead, time lock, first account, deploy that. All right. And then if I switch accounts here, go ahead and copy the address of time lock, and then go ahead and deploy the attack function again with that pointer to the address for the other function. If I just hit deploy, that should work there. All right. So now with our function, we can go ahead and deposit something like 20 ether into the time lock function. So here now we see that we have a balance of 20 within the time lock. But if we want to go ahead and withdraw that, we see an error here, and the error is lock time not expired, which will happen whenever that requirement of the lock time is not met. So what we can do, if we cross our fingers and hope this works, so if we copy this here, all right. So if we copy the address of our account into lock time, we see that we have this large value here, which will be the timestamp plus the 1 week of what our current lock time is. And if we go to our attack function, let's say we attack with 2 ether, then we should be able to say attack here. our balance should be 2. And then if we look at our, our lock time, it should now be 0. And we should be able to withdraw. We do see that our lock time is 0 here, but there's a few funky things with how Remix works. So, but we have successfully kind of overflown the integer, and now the lock time is 0, just by going ahead and adding that, that 1 to it. Okay, so now the next attack, this isn't necessarily an attack, this is just kind of a demonstration of how the blockchain works, or kind of how the Ethereum virtual machine works, and that is, so all variables within a contract are all public, even if they are private static variables, they're still going to be kind of visible by anyone within that contract. So variables within contracts are stored in what's called slots. And so slots can either be 32 or 256 bytes in length. And it will go ahead and from the order of declaration, so top-down declaration, it will go ahead and add these variables into the slots. And it will go from right to left, adding these variables that are declared in, and then each kind of variable has a certain size. So addresses take up 20 bytes, booleans take up 1 byte, etc. And so we'll go ahead and add that the one variable into the slot, in the 0 slot. We'll go ahead and add that into the slot, and then if there's any space left in it, it'll just continue adding all the rest of the variables until that one slot is full, and it'll move on to the next one. So here's what a few different variables look like in Solidity. So we see here that we have an unsigned integer, which will take up the entirety of the 0 slot. And we also see that we have an address here, which we know takes up 20 bytes, so that'll go into slot 1. We have a boolean here, which takes up 1 byte. That'll also go into slot 1 as well. So this is address is on the right, and then we have our boolean is to the left of that address, and then we also have an unsigned integer, which will take up 2 bytes, going left again. So here we just see kind of an example contract. What we're going to attempt to do here is kind of identify the struct for a user, where we want to find their user ID, and we also want to find their password. So we just see here a constructor for whatever the user is, and so it's going to set their password, and also adding a user to memory. Like I said, all data on the blockchain is public, including any of those private static variables. And so those can't be read directly from a contract, so from contract A to contract B. But what we can do is use a really cool thing called Web 3.0 to go ahead and read those variables. So like we used Remix in the other demos, here we're going to use Truffle and a kind of virtual environment known as ROPS. So Ropsten will go ahead and deploy the contract, and then Truffle will go ahead and allow us to kind of interact with those contracts. So at the top here, we see that we are going ahead. At the very top code block, we see that we're going ahead and setting the address of a contract. This is the previous contract that we just saw in the previous slides, deployed on Ropsten. We also see here that we're going to attempt to get a storage address. And so here we see that we're specifying the address of whatever our contract is, comma the slots, and we're going ahead and telling it to go ahead and print to the console. So this is going to print the very first slot, which will be 1, 2, 3. So if we look back at our first example, we see that this is the slot 0 here. So if we just continue going ahead down this line, we're going to attempt to dump the slot 1 of that, and we see that this is 31, or our address here. We can also go ahead and attempt to dump that user's password now at slot 2. So this is going to go ahead and dump the user's password, and we see here that it's in ASCII, and we go ahead and convert that, and we see the password is AAABBBCCC. And so this isn't any kind of privileged access or anything. This is just from my laptop and just straight in a Truffle, and I didn't even deploy this contract myself. This is just a contract already running on Ropsten that I can go ahead and get all this data from. And so these would ideally be users or user IDs that should be private, but we can just go ahead and dump all that information ourselves. So we see here again a hash of the struct. So we can go ahead and dump that. And then we're going to take the hash of the struct and add it with the address. And then we can go ahead and dump that. And as we dump that, it'll continually iterate the hex of that hash. And we go ahead and dump each user ID. So with that here, we see our first kind of password for a user. So this will be user ID 1 of that hash, and that's by adding 1 to that hex hash. And then this will again be the password AAABBBCCC. And so we see here even that struct for the user, we're going ahead and dumping that password from it. And then that's it. So any questions? I know I covered quite a bit. I don't know what I'm doing for time, but. Yes.
So the first vulnerability you identified with like the fallback function, is that like it doesn't seem as much of like implementation specific vulnerability as more of like solidity as a platform?
Yeah, it is. So what you're going to notice. So sorry. The question Brad asked was that the reentrancy vulnerability didn't seem that it was an implementation error, but rather that it was an error with solidity. And so like I kind of mentioned, that error was prior to version 8.10 of Solidity. And so you'll notice with a lot of kind of different smart contract, not vendors, but different languages or frameworks for smart contracts, each one of them is going to have some kind of different, their own vulnerabilities of what the implementation is on the blockchain side as opposed to smart contract itself. So there is another language, I can't remember what it is, but there's something called delegate calls or unsigned delegate calls, I believe. I can say a little more about it later. But what this allows you to do is go ahead and basically shoot yourself in the foot in a way, but then you can go ahead and gain control of others' contracts and then go ahead and basically deplete all their contracts from within them. And so this was a vulnerability kind of discovered within the framework itself, not within the implementations. Really, all you can do within those is go ahead and have some kind of mitigations against that platform-specific vulnerability. So things like not going ahead and waiting until that fallback function occurs to go ahead and set it to 0. So it is definitely a more platform-specific vulnerability. And like I said, that's been mostly patched out since 8.10. All right, any other questions? Yep. Mm-hmm.
Does that mean when you do these attacks, you actually have to, like you were going to do them in real life, you would have to have a certain amount of Ethereum to do certain attacks?
As far as I know, so most of the time, it's going to be dependent on what the pool is and what its kind of requirements are. So that require block, that was specifically requiring greater than 1 Ethereum. So it's going to be dependent on whatever that is, but most of the time it will be physical Ethereum or physical cryptocurrency that's required. I haven't done anything outside of the virtual environments of Remix and Truffle and Ropsten, but I believe that is the case, and it'll most of the time be a lot less than that 1 Ethereum of the requirement. So, all right, anything else? All right, thank you.